Hey everyone. So today we're just going to have a quick little lesson on distributed technology for big data. So this isn't meant to be sort of a super in-deep tech dive into sort of this technology. It's more meant to be like an introduction in terms of like the conceptual difference between sort of computing locally and sort of then the main software that's underlying distributed computation that you guys will be using, and then also to introduce you to just some of a little touch of the language and technology we'll be using to actually go and do this, right? So specifically something called PySpark and Spark over on Databricks. So again, like not super in depth here, but just enough to give you guys a primer, given this is something that you'll inevitably be interacting a lot with if you're either working as a data scientist, an analyst, or a data engineer, sort of whichever way you guys go. So this is probably there. So reminder that we have like tons of data these days, right? So I showed you this figure a while ago, but this notion of just like the amount of data being collected every year is just absolutely booming. And so this is kind of bridging us into the second issue, right? So a lot of this class was this earlier part of doing ETLs, right? So data are often like really messy, and you need to extract it from some source to process it or deal with that mess and to put it into a format that's then useful, right? So you extract, transform it in a way that is useful and load it up somewhere that then an analyst or data scientist or whatever can use it. It's the whole goal of data engineering. But then the other side of that is that just the amount of data has boomed. Like the data is so big now that, you know, you can't necessarily just work locally. So it's a second problem that we've learned about is how do we deal with tons and tons of data? And that's now what we're getting into as a technology that allows us to cope with that, right? So you have the methods in place to deal with the mess. Now let's deal with the quantity. And so here I think it's worth just kind of saying like definitionally, like what does big mean? And so the simplest version is basically too big to fit into the memory of like one machine. Okay, so most of the data that we've worked with in this class obviously can fit into the memory of one machine. You know, it's maybe a gigabyte. I've had some files or multiple sort of, 7,800 megabytes, but still like the computer I'm working on right now has 16 gigabytes of memory of RAM. And then, same with like the cluster that you're working with when you use Colab, also I think normally has around 16 gigabytes as well. So, generally speaking, we're working with data that works very easily on one machine and isn't that big of a deal. And so but what happens when we get beyond that, right? Like when we go beyond this 16 gigabytes, like, so let's say we have a half terabyte file or something like that. How do we deal with that? And so, on the current machine, like I could add more memory and churn through it, right? So I think like enterprise version of Windows, you can go up to like 256 gigabytes or something like that. So, you could just imagine building a bigger and bigger machine or some sort of workstation that can go and just like rip through this kind of really big file of data. You could also imagine some sort of batch processing depending on what it is. So, let's just say you have 100 gigabytes of data and be like, all right, well, I'm going to chop it up into 1 gigabyte chunks. I'm going to go through and do my calculations on that one first gigabyte chunk, then the second and third, and storing those results along the way. And then eventually you'd get through it all, right? And so, these are different solutions, but obviously like this local processing and even just on a single cluster is not necessarily practical for many situations. And so I've talked with, like an associate of mine, where his daily login file that he works with doing security stuff is just a whole terabyte, right? So obviously it's not going to fit easily in memory. And so that's just for one file that he's working with on a regular basis. So that process there is, is it would it work? Again, batch processing might work, but by the time that he actually started executing and waited for results, he's probably leaving for the day, and then he has the next login file that he has to deal with the next day or whatever. So, that isn't effective. If we're looking at Netflix, they have their 10 billion events a day, right? So these are nice and clean data, like they're those raw, like little event. They're raw event data that they just need to process. It's probably pretty simple processing. But it's there's 10 billion of them. It's obviously tons of gigabytes. Facebook is processing tens of petabytes a day as well. And so I have a reference here sort of from Facebook that talks about the amount of their data. And so that's equivalent to 10 million gigabytes of data that they're processing a day. So again, local processing is just completely impractical for this. And this is what that very early article that I gave you is one of the early challenges of Facebook, was that they had this situation where although they wanted to do very simple things like counting how many times the user click something, even in that case, it would take, a few weeks for them with their existing infrastructure way back in 2002 or whatever to actually do that. And so they were some of the original practitioners of, who started using this distributed technology to sort of process data on a daily basis so they could actually use it, right? So data is coming in, they can have a process and pull information out of it right away. And so obviously, like, the solution here is kind of what I'm getting at, and that you guys are probably assuming, if we've heard of cloud computing, and the idea here is that at some point it's just easier to make many machines, right? So, in that early Facebook example, they actually went and set up their own cluster, right? So they made a bunch of different machines, or they linked together a bunch of machines that then were allowed to process at the same time. But like nowadays, you can actually just go to Amazon, and a number of other, Google and Azure and all that, and you can go and just spin up a cluster that has, as many basically CPUs and small machines as you want. So like, here's an example that is a screenshot of one of the different sort of instances that you can create on Amazon. So if you see there's like the GPU and the virtual CPUs and the amount of memory, you can get an extra large cluster with 96 CPUs, and 768 gigabytes of memory, to where you can very readily go and do this massive computation, but you're going to instead distribute the workload across tons and tons of machines that are going to do it at the same time, versus trying to make a single massive machine that's going to do it all on its own. And so that's generally then the approach, right? That's the solution to these really big data problems, is we're going to use lots of smaller machines that then are going to do this at the same time in parallel, versus one machine that's going to do it sequentially. And there's lots of tools now out there that you can do that very simply with. So, but the solution isn't just many machines, and this is one of the key things. It's also this idea of clever computing. And so when I say clever computing, I'm talking about this a specific thing called MapReduce, which was, again, introduced back in like 2004, 2005. And, that article that Facebook is talking about, one of the earlier uses of it, or earlier sort of applications of it, was to process all their data. And essentially what it is that it's a computing framework for dividing up, this computational task across all these different machines that are on a cluster together, right? So if you have, a terabyte of data, how do you allocate that terabyte across, say, 100 different little small machines, so they all do at the same time and manage that? And that's what the MapReduce strategy is, does. And so there's two main stages that we need to know here. And so it's this idea of mapping and reducing, hence the name MapReduce. And so let's just kind of like talk through it, right? So let's say that you have an input of data, and you have a bunch of text, and let's just say you have some simple example of getting a word count. And so you have this text here, so these are obviously very simple, but you could imagine this being tweets, or a Facebook post or whatever, to where you have these long strings of text. And so we want to break that up and figure out how many words are there in each part. And so you start with your input. And so a key thing associated with MapReduce is that data actually need to be stored in a specific format, HDFS. And so HDFS stands for Hadoop Distributed File System. And so there's some key things here that you should take away from this, in that, for one, it's fault tolerant, right? So what HDFS does is it's storing the data, and it's chunked up into blocks that are like 64 to 128 megabytes. There's some things where you can specify like how big it is and all that, and we don't have to do that, right? Hadoop will do that all. Hadoop MapReduce will do that all for you. But nonetheless, it's stored in these blocks that are then replicated across different different nodes on the cluster. So, you have one block that's in 3 different places. So this way, if something goes down, your data is completely fault tolerant, and it can grab it from another cluster, from another part of the cluster, right? From another worker. So we have our data. It's stored in that file system of HDFS, right, on the different cluster. And so the first step that you do is this reduce step. And so the reduce step, the first step is the data are splitted out. So they're split onto, let's say, 3 different worker nodes, right? So we have the top, bottom, and top, middle, and bottom. And so, these then are allocated into those 64 to 128 megabyte sizes. And then after, sorry, that reduce was wrong. I'm not going to redo this whole lecture, but how I say reduce up there, that is not correct. That was an error. So the first thing we do is then mapping, right? So after the data are split up and allocated across the different workers, what happens then is they are, quote unquote, mapped to key value pairs, right? So it takes, this initial format of data and creates this key value pair, basically like a Python dictionary, to where it's then does the action of counting up, the example, in this case, the number of words, so on that first worker, it's like, okay, so for the key of deer, we have a value of 1, and of bear 1, river 1, and then it also then goes down to the second worker, and that worker then also did the same thing, and car 1, river 1, right? And so this is that map part, is that it's mapping this initial data into this alternative format. And then it writes it to disk here, right? So these map values are written to disk. Data are then shuffled around. And so what this does is then it splits up the data to where all the same keys, key value pairs are then allocated on the same worker. And so you can imagine that when we want to go and count this, it's a lot easier if you're not having to move data around to all these different worker nodes, but instead it's already there and ready to go and be counted. And that mathematical operation can happen just locally on that one single node, one single worker node, and then all 4 of them can do it concurrently. And then finally, here's the reduce step, right? So again, sorry about that error there. But so the reduce step comes here at the end, right? And so what it does is you have these key value pairs that can obviously aggregate, right? So the keys are the same, so it can then just simply count up how many times that it's there. And then it gives you the final result. So in this case, the final number of words that are in that initial input. And then this is written to disk again. And so this is kind of like the simplest overview of the notion of sort of how this MapReduce framework works. Is you have your input data, it's stored in a specific format, and it's split up across a bunch of different worker nodes into smaller, easy to process chunks. These chunks then are then, like I said, mapped to associated key value pairs, shuffled around to allow for faster computation than in their little local on the specific worker node, reduced down into the smaller format, and then aggregated into the final format as well. To where you have this final result. And so a couple things about just sort of like the pros of this. So you can obviously process. Not obviously, but the point is you can process terabytes of data, in potentially minutes. So it's very, very simple to just deal with massive amounts of data compared to just a single machine trying to churn through it, because instead you're distributing its workload across tons and tons of computers. It's fault tolerant, right? And so this is pretty important. But so the file system is fault tolerant, but then also if you have, let's say that you had an error in computation or something sort of broke on one of these little workers, it's able to track this and keep track of that, and so your whole process doesn't shut down. It can just redo that at a later part or assign it to another worker node, so it's all managed for you. Whereas if you are working locally on a single machine and it's going and it's computing for a day, and some little error happens, it could actually kill that whole process, which is obviously very, very inefficient and very unfortunate. Furthermore, MapReduce, it also automatically scales to the different sizes of data given the resources available. So if you have tons and tons of data and you have a really big cluster, it will automatically scale and make those decisions for you. There's tuning you can do beyond it, but just sort of in its naive form, it'll do this all for you and allow it to very effectively churn through a lot of data given what resources are available. Again, tracks what each node is doing, so fault tolerant. And the thing that's important to point out is it can do a lot of things, right? So it's like, this algorithm can go and it can do all your SQL queries, it can do data wrangling, machine learning, etc., right? So this computational framework is really effective for sort of all these critical things that are necessary for data engineering, data analytics, and data science, right? And so that's why you'll see, in most job ads, people are going to want to know that you're at least familiar with and have some light experience with MapReduce, sort of at the undergraduate level of hiring. You've heard me accidentally say Hadoop once, and so I want to point out that when you see Hadoop, it's people kind of use these interchangeably. They're like, oh, you should be an expert on Hadoop, and so it's actually it's what people tend to mean is that they tend to mean when they're talking about sort of the distributed computing part using MapReduce, right? Or you're familiar with this MapReduce process, the algorithm that does this distributed computing, right? And then so just sometimes you hear those things used interchangeably. And so what I want to talk now about is we're actually not going to use Hadoop MapReduce. We're going to use Apache Spark. And so I want to just sort of do a little compare and contrast of what these two are and why we're going to be focusing on Spark. And so MapReduce came out first, right? But Spark can be 100 times faster than MapReduce. And so this is for just a very simple reason, is that essentially it's doing everything in memory, right? So MapReduce will have multiple writes to the disk, where Spark is leveraging the fact that memory is cheaper and cheaper now, where before disk space was really cheap, and disk space still is really cheap. But so Spark leverages the fact that we have pretty expansive memory. And so instead of doing all these writes to disk at different stages, it just churns through it all and gives you the results back, and you can write to disk at the end. Another reason why Spark is kind of becoming preferred and is rapidly sort of taking over, or has taken over, is this notion that MapReduce needs the HDFS file format, where Spark can take in a huge range of file formats just right off the bat. So it can take data from HDFS, S3, Blob, and like a whole host of other data sources. So you don't necessarily need this very specific format of data, which is obviously really useful. It just makes it easy. It's so easy to put data and store data on S3. And so data can be stored and uploaded there and then processed right away automatically in sort of this big distributed framework. Downside to Spark is it's more expensive, right? So I said before, memory is cheaper, but memory is still not as cheap as hard disk space. And so, it still is a little bit more expensive to potentially run Spark, which may or may not matter depending on the resource of your organization or the size of data that you're going to be using. A perk to Spark is it's really easy to code, right? So you can code via PySpark, but you can also readily use R, Scala, and Java. And so that's what I was saying there. So, but the PySpark allows you to use a very Python-centric framework, because obviously it's for Python, to code Spark code. Versus MapReduce, which sort of is a little trickier, right? So, but PySpark is this very well supported API with good machine learning libraries and all this sort of stuff. So that's why we're going to be using it. We'll be learning PySpark in order to use Spark. So again, PySpark, what is it? Python API for Spark. So Spark data frames are nice because they work really similar to pandas, and the syntax is really similar. So if you're comfortable in pandas, which hopefully you are by at this point, it won't be too much for you to sort of figure out some of the little differences that's in syntax. And there's also a SQL syntax too. It has a very expansive machine learning library. And then the thing that I like the most is that it's very easy to use Jupyter-like services, right? So there's a lot of these out there. So the two that we'll consider, on only one we use, Amazon EMR, so it stands for Elastic MapReduce, and Databricks. And so both of these use Jupyter-like sort of notebooks, but then readily can access and utilize the Spark computing framework. So Databricks, for example, is what we'll be using. And so Databricks was founded by the creator of Spark. And so this way it's a nice, easy to use, ready to go thing. It uses Jupyter style notebook. You can use a bunch of different types of code in it. But the thing is that it really easily connects to clusters, right? So you can have clusters that you set up there or on Amazon or whatever, but so you can easily connect to however much you set up size-wise. And so this way you have all these computing resources at your hands. The other nice part about Databricks is that many companies already use it, right? So it's becoming something just like Amazon EMR. Databricks is something that companies are using for sort of this like really simple turnkey solution. Like you can go log into Databricks and your cluster's there, you can connect to a database or whatever, and like really start coding right off the bat without a lot of like infrastructure to put in place. So even though it might be a little more expensive, when you look at the fact that a company is having to manage all this or set up all these individually, like just going to go log into Databricks and start using it right away is pretty powerful and important. And the last thing about Databricks is it's free, right? Or at least for us. So there's a free community edition. The link is right there. So what you guys are going to be doing, and this is how we're going to be working in this class, is you're going to go log in, you're going to go make your account, and it allows you to use basically a Google Colab style size cluster. So I think it's like 2 CPU cores and 16 gigabytes of memory or something like that. But so enough that we have a cluster that's ready to go. And the other nice part is that PySpark is ready to go, right? So Spark is on there and all the necessary underlying infrastructure is on there. So we're able to just boot this up and get running right away and doing distributed computing stuff. And so that's what we're using for this class. So what I want you to do in this lesson is go to that link, go get your account set up, and then tomorrow you'll be getting a notebook where we can then actually start learning how to code in PySpark. Thank you for listening. As always, make some comments in Slack or here on the YouTube channel. Thanks.